Благодаря. So it's a pleasure for me to be here and a big honor because I started programming Ruby exactly 20 years ago. I think I wrote my first production code in May 2006. And I would never imagine that 20 years later I will still be doing programming in exactly the same language. So my presentation today is it's a fruit of not just professional experience, but I was for a few years part of the team that taught Ruby in the Sofia University. And the best way to learn something is to teach it. So I learned a lot while teaching, and my first lecture there started with, a false start, because I was to explain the foundations of object-oriented programming and why it is still relevant. And I discovered a talk by Rich Hickey, the guy that created Clojure. And I just realized that many assumptions that I had about object-oriented programming were actually quite false. And I felt like a scam artist in front of the students. So this is like, this lecture now is I'm trying to repay this karma. And I'm going to talk about not only the roots of the object-oriented programming, but how it was supposed to happen, to be, and to show that it's actually not the original idea behind the object-oriented programming is not much different than the foundations of the functional programming. So with this, let's get started. I first want to say that I identify myself as a programmer, not a software engineer. And I studied a lot with the Department of Logic in the Sofia University, so I have a mathematical background that sometimes collides with the the programming is sometimes engineering, and you have to do the things in an ugly way, dirty and quick. And I prefer to do it in an elegant and better way that sometimes is not what the client wants, because they pay us for delivery and not for elegance. Anyway, so a year after I started programming Ruby, together with Denitsa, we founded a company, Tutuf, and we're still together. Our company is very tiny. We're just 3 people at the moment. We finished, these days, we're about to finish a project that we started in 2009. And it was our only project for the last 17 years. So we're now open for collaboration. If you have some ideas, if you like our talk, and if you like the games, you can come and talk to us, and whatever you can say hi at tutuf.com if you later want to contact us. And a very important thing is I want to ask you before I start this presentation, because this is Balkan Ruby, I want to ask you who is from the Balkans as of origin. Please raise your hands. And who identifies as Balkan, no matter where they are from. So, okay. So for those people that didn't raise their hands, I want to tell you that first you should know that the Balkans are the most of everything, the most ancient, the most ugly, the most beautiful, the best, everything is to the extreme on the Balkans. So, no power. So keep that in mind, don't get offended, because, you know, civilization started on the Balkans, and the first hominoids that came to Europe, they came through the straits and they established themselves on the Balkans. And this is a map that actually shows the real Balkans, not just the geographical distribution. I don't know why Spain is omitted from this, but I'm not the author. But for me, Spain is also Balkan. So let's go back. You know, the famous American scientist Carl Sagan, who was very popular in socialist Bulgaria, he had a sentence that if you want to create a sandwich from scratch, you have to start with the universe. So if you want to understand programming, we have to understand math first. And to understand math, we have to go back to the dawn of humanity to see how it all started. So it seems that it all started with this unassuming piece of artifact. It's a bone that was discovered in the Kozarnica cave in northwest Bulgaria by Bulgarian and French archaeologists 30 years ago. And it has the oldest counting marks that were purposely made by a member of the human species family, Homo erectus. It was in a layer that was dated about 1.4 million years ago. And these marks are the first thing, I mean, before this discovery, it was assumed that the first abstract thinking was the first drawings or some first symbols were used by the Homo sapiens, but it seems that we have to, after this discovery, the whole prehistory of humankind has to be rewritten. And because they didn't serve any functional purpose, any utility. So to understand abstract, we have to go to the word. It generally means something that is not specific, that is not concrete. It doesn't have a body or doesn't have a material presence. It is some kind of a universal. And it also is extraction of something or summarization of something. And etymology, it means, the Latin etymology says that it is something that was taken out of something else. And abstract thinking continued to develop in the prehistory. And one of the longest, again, the most ancient examples of abstract art can be found in the Magura cave, again in the northwest Bulgaria. It's rather close to the Kozarnica cave. This can also be considered as the first comics. It's a graffiti that is, scientists argue how old actually it is, because it was in the 1960s. It was made with guano bud in a part of the cave that was artificially closed by the prehumans, by the humans in prehistory. So they wanted this to be preserved. But how old it is, nobody can say, because in the 1960s, they painted it again with new guano, and the radiocarbon method of this new guano said that it's about 3,000 to 5,000 years before present. But according to some researchers, looking at the erosion marks and other things, it might be up to 40,000 years before present. So nobody knows. And also, this kind of cave art was discovered all over Europe and Eurasia, and the symbols that were used, Swiss anthropologist named Genevieve von Petzinger made an extensive library of them, and in the Magura cave has the biggest set of these symbols. Like 96% of them were present there. And this example that I'm showing is just a part of the whole gallery murals. And they were amateur researcher mapped them and counted them, and there are more than 1,000. And most of them are unique. Some of them repeat, but they repeat in a very different way. So this amateur researcher tried to decode this work. I don't say that it is, I don't endorse this. I just say that I show it as a kind of a way to read this. So obviously this is some kind of abstract message. We don't know if this is true or it is not, but still it contains a lot of symbols that are shown in a way that it's really not like the cave art that we are accustomed to with animals and real-life depictions. So it must be some kind of message. Maybe not this, maybe something else. We will never know. So it's also, this picture is quite complex. It contains a lot of elements. It has human-like figures, chessboard-like fields, a sickle that is collecting something, the letters, the modern letters of Latin alphabet, T, I, O at least, and some other symbols that look rather abstract, that we don't know what they were used to depict. So this brings us to the cousin of abstraction, complexity. And complex, it's also a word of Latin origin. It means something that is intertwined, something that is braided together. It's a plex, in the word, it means to braid, to twine. So you have things you take together and you braid them. And I was very surprised to learn last year after the presentations, we had a discussion with our first intern in our company. And it seemed that even intelligent people nowadays don't understand that abstract and complex are completely different things. Something can be abstract, but might not be complex, and something may be complex, but not too abstract. And I'll give you an example that is rather simple with the Roman numerals. And let's try to depict the last year of the previous century in Roman numerals. If you are going to movies and watch all the titles after the movie, you might have seen this at the end with the copyright notice. This is the canonical representation of 1999 in Roman numerals. It is what the Romans used in the past. It's like much like the present positional system that we used. So M means 1000, CM is 900, XC is 90, and IX is 9. But this is only one representation that is valid. This is another valid representation. So 900 here is D, C, 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 C. And we can expand the 90 in another way. So it's L, X, 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 X. And there are many other representations that are valid. So you see that the Roman numerals, although a bit abstract, they are quite complex and difficult to navigate. On the contrary, the Indian, or as we know them, Arabic numerals, they have a very simple representation of the same number. And it is because they are more abstract, because they have another rule that says that each symbol, each number depicts a power of 10 depending on the place which it appears in the number. If it's in the first place, in the last position, it's the power 10 to 0. So it's the number by itself, the digit by itself. So if it's in the second position, it is tens. In the third position, it's hundreds, and so on. So we see that if you have a simple rule and an abstract way to represent things, you can build something that is much more elegant and less complex. And to put it in another way, abstract and complex are orthogonal conceptions. They don't, something can be complex, but not too abstract, and something can be quite abstract, but simple. And with that said, we can go to our field, the field of computers. And I would like to ask you, can you guess when was the first known to the humanity computer made? Can somebody make a wild guess? Like, when was the first computer produced? Sorry? Define? Computer is a device that computes things. Sorry? Okay, we have a winner here. So this is the Antikythera device. It is 2,200 years old. It was, and let me not forget, we're on the Balkans, to establish a fact. It was discovered in the waters of near the island of Antikythera, which is in Greece. Greece is on the Balkans, so the oldest computer is Balkan-made. And it was a device that initially, it was not, when this was discovered in the beginning of the 20th century, nobody thought it was just a lump of metal at the bottom of the floor, very corroded, not precious metal, so nobody put attention to it. And in, I think, 1960s, somebody decided to investigate it, to X-ray it, and discovered that it has an elaborate system of cocks inside it. So it was restored, there were some schemes made, and finally it was discovered that this thing was a device that could predict solar eclipses and show the exact position of sun, moon, and planets that are visible by plain sight. That is Mercury, Venus, Mars, Jupiter, and Saturn. So this is the oldest computing device, and obviously it is an analog device. So it's this plate is the actual display. That this is the UI. That it displays the position of the planets on these orbits. So this is an analog device. You input the dates, I mean the current position, and when you are turning this dial, you move the planets and you display some position in the future. So it has analog inputs, analog outputs, and now digital computation to come inside. But these cocks actually they do the real function computations. So with this said, I want to ask you, who used an analog computer today? Even unknowingly? Nobody. So maybe I didn't ask properly. So who came here by car? Can you raise your hands? Only one person. Who came by public transport? Very nice. So all these people that raised their hands, they used an analog computer or a device that used an analog computer to do its job. And the analog computer in this case is this one. This is the most common type of analog computer today. This is the valve chamber of the automatic transmissions that are found in practically all the cars, at least in the public transport. The buses and trolleybuses work with this. So how does it work? There is an oil that goes inside, and depending on the pressure, which depends on the turning cogs that drive the transmission, it flows through this labyrinth and it changes the pressure. So when it creates less pressure, the cogs move in one direction. When it creates more pressure, the cogs shift to the other direction. So that's how the automatic transmission changes. And this is actually, this is the functions that they compute. And practically this device is functional programming that was set in hardware. So this is about how the computing started. It started with analog devices, and let's go to a bit more modern times, how the modern computing started. It all started with maybe a bunch of guys in the United States, and this is the most famous demo of all times. It's called the mother of all demos. This is Douglas Engelbart showing the first computer, the first mouse. He holds the mouse in his right hand, sorry. There is a keyboard on the console between his hands, and his left hand is on a device that no longer exists, unfortunately. It's complementary to the mouse. You can input commands with it that are complementary to the mouse. So it's like extra mouse buttons. And this was done in 1968, and it was really revolutionary at that time, because computers at that time were programmed by switches or by perfocards, and consoles were just appearing, like text consoles. So they jumped one generation ahead, and what he showed in 1968 was successfully implemented in the 90s, because the hardware at that time didn't allow for such extravagant interfaces. And this is the first visual interface that was created in Xerox PARC. This is the mother of Macintosh and Windows. Both Steve Jobs and Bill Gates went to Xerox PARC and saw this, and they implemented it in their operating system. But what is interesting about this interface, that it was created with a very innovative programming language. The programming language is Smalltalk. It was created by Alan Key, and he is the person who coined the term object-oriented programming. So nowadays, everybody understands something different by this term, object-oriented programming, but I want to reproduce the words of the inventor of the term. This is him, by the way. So he said that the original conception had several parts, and his main inspiration were biological cells. The most interesting thing about cells is that they have a membrane. So this is this part that separates them from the outside world. And everything that comes from the outside, in order to go to the inside working parts, it has to pass through the membrane. And the membrane is very selective. It lets some things pass and some other things not pass. So this is how, for example, it is a barrier to other cells, like not friendly cells, like viruses and bacteria. But it also stops certain chemical compounds and lets other chemical compounds enter. And this is how our body functions, because different cells are sensitive to different chemical molecules. And this is how the brain works. In that case, the neurotransmitters that carry the messages are taken by the neurons, but not by other cells. And the second point that Alan Kay made was that he wanted to get rid of data. So this is kind of very confusing statement. And he was asked to clarify it. And because he's very active on Quora, I could find his answer there. So he said that actually what he meant is that in the original procedural programming of the mainframe era, data was something that was, because of the constraints of the memory constraints of that time, it was something that was actively mangled. It was constantly changed. So it was messed up with. And this led to most of the programming errors bugs came because some program that was not supposed to mess with some data was messing with it, just by incident or unintentionally. So in the second sentence, you can see a critique of the so-called modern object-oriented languages, because most of them permit setters, Ruby included, which means that the data is not really encapsulated. Somebody can mess with it from outside. And this is what Alan Key explicitly wanted to avoid. He said that his biggest mistake was calling what he did, object-oriented programming, because he said the objects are not important. The most important thing are the messages, the way they communicate with each other. So the object, according to him, should be something that is encapsulated, something like the cell that nobody has access to this, except viruses and some malevolent actors that go inside. And this is how actually life functions, because without the membrane, we wouldn't be this, we couldn't evolve like these complex beings that we are. So this is evolutionary tested, like billions of years of evolution show that it's right, and I think copying nature sometimes can be a wise thing to do. So with this detour about data, let's see what actually data is. And there is one definition can be that is a kind of it's an observation or facts that we gather about our surroundings at certain point of time. And this is important because facts change, like depending on the time of the day, the temperature changes or whatever. So the second thing that is important, and it can't do anything else. It doesn't have side effects. And this is what we see with objects. With objects in modern object-oriented programming, they can have very much side effects. And these side effects, if you have a complex application in Rails with active record, you have seen these side effects many times. And for example, they have beaten me very badly in the 20 years ago when I had nested attributes, before nested attributes existed in active record, and I had to always try to find the proper object that contained all the attributes and not some newly produced object that didn't contain them. And there is a third thing about data, the fact that when a fact is established, it doesn't change. That's why it's important to, at the first point that we have, that is fixed to a certain point of time. What does it mean that it doesn't change? For example, the number of air molecules in this present moment in this building is, let's say, 3 billions or 3 trillions, and this fact doesn't change. Next minute, they may be a bit more or a bit less, but at the point of time when this fact was recorded, it is established fact, so it doesn't change. And this is what is really what makes most of the programming mistakes when they change what they're not supposed to change. And if we go back to, to the object-oriented programming as it was imagined by Alan Key, which is, in his words, that he didn't want to do imperative programming. He wanted to do request programming. So it's important that the messages that we send to the objects, they're not commands. So the whole thing with domain-driven development goes out of the window with this definition. I don't know what is your opinion on domain-driven development, but for me it contains some very ugly parts, and one of them, this is the command interface. The other thing is the object, how the classes, how they are named. And with this said, let's go to see some examples of like what is important in functional programming, what makes it so good and superior to other paradigms of programming. So immutable data is one of those things. When you have data, you don't change it. It's always the same. If you need to process it, you produce new data, new facts that are based on those facts, but they're new, and they can be clearly distinguished by the original, from the originals. You can also compose functions. Functions in functional programming are first-class citizens, and you can do many things with them, like you can treat them as data, which gives you extra powers. And there is no shared state. And I don't know what is your opinion on state, but for me, the state is one of the roots of all evil. You can read the state in any sense. So, Ruby is a multi-paradigm language, and one of the paradigms that it supports is functional. And let's see some of the features. Everybody knows blocks. They are actually anonymous functions. They're not something special. I mean, they're treated in a rather different way than, I mean, a slightly different way syntactically than pure anonymous function, but they function, they actually pass some function. And this is an example from my favorite functional library that can be found in every project. It's rake, and this is a tiny rake task that does something simple. So task is a method that takes it takes a block, and this block is depicted with this do and this end. I think everybody knows this who programs Ruby, but my brother is here, he doesn't know Ruby, so I explained this for him. And another feature is we can explicitly pass anonymous function when we need, so that we can change behavior or request something to be executed at center point asynchronously. And this is an example that we can see from the Faraday library, which is used to make HTTP calls, HTTP requests. And you see here, retrieve argument takes a lambda. Lambda is an anonymous function. So we tell it to do something later. So this is called late binding, a very important point in functional and object-oriented programming. And also there are something that if we try to start programming in a more functional way in Ruby, we can go into to deviate from the proper path and fall into some traps like the procedural programming. We can have classes that have no initializer, so practically then they don't instantiate objects, and we can treat them like modules. We can call them class or a module, it doesn't matter, and we can do something with data in them, like use them as a collection, as a module of a collection of functions. But this can lead to actually, when we mutate the data, we do actually procedural programming. This is not functional. We change the data that is passed to us. And this is my example from the event sourcing, from the data domain-driven programming. There are certain libraries that ask us to make events, certain events, as classes. So this username set, it's the event that happens, but this is actually data. And the way they function, I think this is some kind of a legacy from other languages that I don't want to name. They start with J or C and have other letters. And actually this can be shortened, made in a more simple way that we don't hide this piece of data. We just send it as a pure data, not something, we don't hide it in a class. So I want to finish with the words of a wise woman, that all that we have, that we're talking about, that is our worldview is set on, is some paradigms, be it object-oriented, functional, or other paradigms about how we see the world. And she wrote a small leaflet about the leverage points that you can use to change a system. She's part of the Rome Club that they created one of the most complex abstract models of the world and used it to try to predict, to see how the society will be in the future if we don't change our path of our business as usual. And she said that every leverage, she named 12 leverage points and said that the higher you get on this ladder, the more power you have with the lever to change the system. And the second to last was changing the paradigm, like what happened here in 1989. We changed the paradigm. We were a socialist country that was about having a planning commission set the prices, which led to economic catastrophe. And we changed the paradigm in 1990. We became a free market society. And a lot of things changed, as you can see. But the leverage point that is even more powerful than changing the paradigm is that realizing that paradigms are also a set of points that fix you to a certain worldview. And if you transcend them, you can be truly free. And she was not a religious person. She was a mathematician, trained that she was educated in MIT. She was a PhD. And she said that actually we should be, transcending the paradigms is what Buddhists call enlightenment. And as a Buddhist, I would say that she was right. So that was everything for me. Thank you very much for your attention.